Hey guys, time to start a new unit. So we're talking all about gases in this unit. And hopefully you already know a lot about gases, but this will help us to take what we know about them at the macro level and, as always, talk about them at the micro level. So we're going to start our discussion by talking about pressure and how that relates to gases. So I'm going to share a PowerPoint with you and we're going to talk through it and we'll do some practice problems. And then if you have questions, you can always contact me or Mr. Sanford or Mrs. Bolton, whoever's appropriate. So let's jump right in. Okay, so when we start talking about gases, we're going to talk about something fairly familiar, an awful lot. We're going to be talking about balloons. So they're a great way to talk about gases. So let's jump in and talk about pressure. You guys might know something about pressure already. So at the end of today's class, you guys should be able to talk about what standard temperature and pressure are for gases when we talk about them in the chemistry class. And we're going to talk about being able to define pressure and describe how it's measured. You're also going to be able to convert between different units of pressure. So let's start with what pressure is. So according to the physicists, pressure is a force distributed per unit area. And so we have this picture of a ballerina, which might not make a whole lot of sense in a chemistry class, but we always like to talk about her because if we think about a ballerina, her weight does not change. Weight is a unit of force because it's mass times gravity. And so we are going to talk about the weight of the ballerina doesn't change, but when she goes on point, the amount of pressure on the floor that she's exerting is larger because when she's flat-footed, she has a certain amount of weight distributed over a wider area. And when she goes up on point, she takes that same weight and she distributes it over a smaller area. And that's going to become important to us as we talk about pressure with gases as well. So let's just hold on to that definition. And I'll give you guys a minute to write it down. And then we're going to talk about how pressure is exerted by gases, because we don't tend to think of gases as having a lot of mass. Because each individual particle is very small and they're very spread apart, but they do have mass and they exert force by colliding with things. And so when we talk about pressure with gases, we talk about the pressure from a gas is caused by the collisions of the molecules with the walls of a container. Now, when we talk about atmospheric pressure, we're not necessarily talking about a gas in a container. And so when we talk about atmospheric pressure, we are talking about the mass of the particles times the acceleration caused by gravity, and that's their force. It's really about the weight of the particles bearing down. And there's a lot of particles between us and our exosphere, and so that does exert a fair amount of pressure. So when we talk about pressure, if we go back to our example of the balloon, so obviously this is a helium balloon since it's floating. And so inside our balloon, we have lots of helium molecules, and outside of our balloon, we have lots of air molecules, and air is a mixture. So those air molecules are colliding with the balloon, and inside the balloon, the helium molecules are colliding with the balloon. So the pressure inside the balloon and the pressure outside the balloon are the same. If the pressure starts to change, the size of the balloon is going to change, but we're going to come back to that when we talk about gas laws. So for right now, we know that the pressure, the force that is being exerted over the area of the inside of the balloon is being caused by the collisions of those helium molecules with the walls of the balloon. So how do we measure pressure? We have this lovely picture of Evangelista Torricelli. We measure pressure using something called a barometer. And the barometer was developed by Evangelista Torricelli in the 17th century. Barometer comes from the Latin words for weight and measurement. And so Torricelli developed this as a way of measuring the weight of the air molecules. And so let's take a look at a picture of a barometer. So early barometers looked like this. If we ever get back to school, the one in our classroom looks a little bit different, and we can talk about that one in the classroom. But early barometers were open dishes filled with mercury. And into that dish of mercury is inverted a closed tube with nothing in it, not air, nothing. Okay, and what happens is that the air pressure, the weight of the molecules of air between us and the exosphere, pushes down on the surface of the mercury. And when it pushes down on the surface of the mercury, it pushes that up into the tube. At standard atmospheric pressure at sea level is 760 millimeters of mercury. And that's because at sea level, the weight of those air molecules is enough to push 760 millimeters or 76 centimeters of mercury up into that tube. Now, barometers use mercury because mercury is extremely dense. We could do the same thing with water, but we would need a tube that was 13.6 times taller. And so it's not very practical for us to have a water barometer. There are some out there, but a water barometer is not particularly practical. The 760 millimeters of mercury fits nicely onto a tabletop device or a wall-mounted device. So let's talk about some units for pressure. So our first unit for pressure is the one we've already talked about. That's the millimeter of mercury. And this is the pressure unit that's derived from the barometer itself, from experimental measurement. And so we define 1 millimeter of mercury as the amount of pressure that supports 1 millimeter of mercury in a barometer. You'll notice down there at the bottom that there's also a unit called a torr. This is named for Torricelli, the guy who invented the barometer, and it is equal to 1 millimeter of mercury. So those two units, though they have different names, are equal to each other. The unit that we'll use the most is the atmosphere. The atmosphere is the average atmospheric pressure at sea level and 0 degrees Celsius. It is 760 torr, or 760 millimeters of mercury. The one that we will use very rarely is the Pascal. A Pascal is actually the pressure unit in the SI. Remember our Système International that we learned about at the beginning of the year. And a Pascal is 1 Newton per square meter. We don't use the Pascal very often because it's actually a very small unit. When we do use a variation on the Pascal in the chemistry classroom, we tend to use the kilopascal, which means it's 1,000 pascals. So those are our 4 units: atmospheres, millimeters of mercury, torr, and pascals or kilopascals. We will add one more, and that's the one that you guys are probably most familiar with because it's the one that you use in your everyday life. If we're measuring the pressure in a tire, we measure it in pounds per square inch, or PSI. So standard pressure. So all through this gases unit, we're going to talk about standard temperature and pressure. So standard temperature and pressure requires that 2 conditions are met, one for temperature and one for pressure. So let's talk about what standard pressure means. So standard pressure is 1 atmosphere, or if we were to convert it, it's 101.3 kilopascals, or we could also talk about 14.7 pounds per square inch, or PSI. It's 760 millimeters of mercury, or it's 760 torr. Those are all the same thing. Okay, so standard pressure is any one of those because those all describe the same amount of atmospheric pressure. Let's talk about temperature. So you guys remember when we talked about metric units and SI units that we normally measure temperature in Fahrenheit. Most of the rest of the world measures temperature in Celsius. And then we said that there's this SI unit, Système International unit, called the Kelvin. And the size of the Kelvin and a Celsius degree is exactly the same. And so the difference between freezing point and boiling point in both of those scales is 100, whether it's 100 degrees Celsius or 100 Kelvin. Fahrenheit has 180 degrees between its boiling point and its freezing point. And so the size of its degrees is actually much smaller than either a degree Celsius or a Kelvin. Now, in the chemistry classroom, we don't use Fahrenheit very often, so we're not going to worry too much about that one. You guys do need to know how to be able to convert between Celsius and Kelvin. And so if you have a temperature in Celsius and you want to convert to Kelvin, you're simply going to add 273. If you want to go from Kelvin to Celsius, you're simply going to subtract 273. So this is one of the easiest conversions that we do in chemistry. You just have to remember that 273. All of our problems as we work with gas laws, all of the problems in this unit are going to require that temperature is in Kelvin. Okay, so it's really important that you guys remember always through the gas unit that we talk about temperature in Kelvin. So standard temperature, remember we said you have to have standard temperature and pressure, is 273 Kelvin, or it's 0 degrees Celsius. So that means that standard temperature and pressure is 273 Kelvin and 1 atmosphere, or it's 0 degrees Celsius and 1 atmosphere, or it's 273 Kelvin and 760 millimeters of mercury. I think you guys get the idea here. A pairing of any one of those is considered standard temperature and pressure. Okay, let's talk about how we convert pressure units. So when we go to convert pressure units, we need these conversions. 1 atmosphere is equal to 760 torr, 760 millimeters of mercury, 14.7 pounds per square inch, or 101.3 kilopascals. So let's do a practice problem. So if we wanted to convert 785 torr to atmosphere, the first thing we need to figure out is what's our conversion factor. And so our conversion factor is that 1 atmosphere equals 760 torr. So we're going to start with our 785 torr. We start with the given, and then we're going to multiply by a conversion factor. Now, since what we have is torr and what we want is atmospheres, we're going to make sure that in our conversion factor, what we have is going to be on the bottom and what we want is going to be on the top. And so we're going to multiply this by 1 atmosphere over 760 torr. Maybe. So let's try this again. So we're going to multiply this by 1 atmosphere over 760 torr, and that's going to give us 1.03 atmospheres. All right, so if we want to convert 122 kilopascals to atmospheres, we're going to go through the same process. First, we need to remember our conversion factor. So we look that up and we find that 1 atmosphere is 101.3 kilopascals. Because I'm having slide difficulties, we're going to switch to this. Okay, so we know that we have 122 kilopascals. Oh, that's backwards. That's not going to work. Okay, let's try again. So, one last time, we'll try these practice problems. So, here we are in our practice problem. We have 122 kilopascals converting to atmospheres. And we know that 1 atmosphere equals 101.3 kilopascals. So we're going to start with what we know, 122 kilopascals. And then we want our conversion factor. So we're going to put kilopascals on the bottom and atmospheres on the top. There we go. So we have 101.3 kilopascals on the bottom and 1 atmosphere on the top. So we're going to divide 122 by 101.3, and we will get that we have 1.20 atmospheres. Remember, because this is a conversion factor, that 1 atmosphere is an exact number, and it doesn't affect the conversions, or it doesn't affect the significant figures, sorry. So we have 3 significant figures to begin with and 3 significant figures at the end. Okay, one more practice problem. If we want to convert 2.4 atmospheres to pounds per square inch, so now we're going to use the conversion factor that 1 atmosphere equals 14.7 pounds per square inch. So we're going to start with the 2.4 atmospheres. So notice this time we're starting with atmospheres. And so we're going to put atmospheres on the bottom and pounds per square inch on the top. And so we have 14.7 pounds per square inch over 1 atmosphere. So the atmospheres will cancel out. We'll multiply 2.4 by 14.7, and we'll get 35 pounds per square inch. Notice this time that I started out with 2 significant figures in 2.4 atmospheres, and so my answer of 35 pounds per square inch only has 2 significant figures. One last practice problem. If we want to convert millimeters of mercury to atmospheres, so I'll give you a minute. Let's see if we can remember what the conversion factor is. So 1 atmosphere is 760 millimeters of mercury. One last time, we'll start with 832 millimeters of mercury. And then our conversion factor, we're going to put millimeters of mercury on the bottom and atmospheres on the top. So we have 760 millimeters of mercury on the bottom, atmospheres on the top. Millimeters of mercury will cancel out and leave us with atmospheres. So our problem is 832 divided by 760, which gives us 1.09 atmospheres. So I hope this is helpful. If you have any questions, as always, contact us. Go Saints!